All right, so we're going to go back and we're going to look at this equation and how to use it in solving for the variables that we need to understand our signal. So again, our signal looks something like this. And what we want to do is define the frequency, define the period. We want to know what T1 is. We want to know what T2 is. We want to know how to get those variables. And we want to know what the duty cycle is. And the duty cycle is the percentage of time on. So, we've already done a little bit of this in the last video, but we're going to do the complete thing here. So, our frequency, which is 1 over our period, is equal to 1.44 divided by, I'm going to use the numbers that we used in the last video, which was, and these are right out of the spec, 3.9K, which is RA. Whoops, I do not want that there. 3.9K plus 2 times 3K, and then all of that times C. This is RA, this is our B, and this is our capacitance, C. These values are normally given, so you can just use the values. At least that's how we're going to do it. Now we do our math on here. Use your calculator the proper way. We've talked about making sure you understand how to use your calculator. You do it the proper way, and you get a frequency. We've already calculated it at 14.5 kilohertz. Now, if we take that, that's our frequency. And we know that our period is 1 divided by the frequency. We do our number here, which is very simple, 1 divided by 14,500. We end up with 68 microseconds. Okay. So we have a 68 microsecond pulse and a frequency of 14.5 kilohertz. Important information to understand. Now, if we flashed an LED with this pulse, we wouldn't see it because this is way too fast. But for the sake of just crunching the numbers with the circuit, with the equation, we're just gonna go with these numbers. They're in the spec and they're easy to understand. So we know now that we have a pulse that looks like this. Where one cycle is 68 microseconds. What we don't know yet is what T1 is or T2, how much time we're on, how much time we're off, and the duty cycle, which we're going to calculate right now. If we look at the spec, T1, 0.693 RA plus RB times C, which is easy to plug into your calculator, and this one, T2, even easier to plug into your calculator. So if we were to put these numbers in, our T1 then, our T1 would be 0.693 times RA, which is 3.9K, plus 3K, which is RB, and then let's make sure we go back, times C. And our C was 0.01 microfarad. Now make sure you get the root number or the raw number like we've talked about many times. This would give us a T1 if you plug that into your calculator of about 47.8 microseconds. Okay, that's an important thing to know. That's that number right there. Now our T2 is equal to 0.693 times our B, which was 3K, times C, which is 0.01 microfarad. And again, those numbers, once again, came from right here, right on the spec. So if we calculate those numbers, we get a T2 of about 20 microseconds. Now I gave you these numbers in the last video, but we're calculating them now just to make sure that they are correct. So again, looking back at the spec, and we can double check ourselves, looking back at the spec, we know that the T1 plus T2 is equal to T, and we have this equation out here, but we already have these three numbers, so we can go back and double check. T is equal to T1 plus T2. We were at 47 microseconds plus 20 microseconds. It's going to give us 67 microseconds, which, if we look, is pretty close to what we had calculated up here. So we're good. We're close enough. 67, 68, we'll take it. It's close enough. Okay? Now we want to know what the duty cycle is also. In the duty cycle, if you look on the spec, RB divided by RA plus 2RB. RB, which was 3.0 K, divided by RA, which was 3.9 K, added to 2 times RB, so 2 times the 3K. Again, you put that into your calculator and you put it in properly, you're going to get about 70%. All right, so what does all this information mean? I'm going to zoom out here a little bit. What do we know right now? We know that our frequency is 14.5. We know that our period is 68 microseconds. We have a T1 of 47.8, a T2 of 20, and a duty cycle of 70. Well, this is what it tells us. I'm going to zoom in a little bit. What it tells us is our pulse looks kind of like this, where T1 is 47.8 microseconds. T2 here is 20 microseconds. That's a 2. So really our pulse is on twice as much as it's off. And our duty cycle tells us we're at 70%. So our period here, T, which was 68 microseconds, out of that 68 microseconds, 70% of the time we're on, and then that would mean, of course, 30% of the time we are off. And this is all while going at a speed of 14.5 kilohertz. That tells us everything we need to know about this equation. I'm sorry, about this waveform. It's important, basically, because when we design a waveform, and we use the Astable to design it, we have to understand what we're trying to do. So if we have an LED, in this case, we're obviously not going to see it flash because this is happening way too fast. But if we slow this down, if we create a pulse, which you're going to do in your assignment, if you create a pulse, maybe it's on for 1 second and off for 1 second, something like that, then you can actually see this blink. Or if you want it on faster or off faster. Totally up to you, totally up to the designer. But these are all of the equations and how we get there. All right, so you're going to have an assignment. You're going to have a quiz first, and then you're going to have an assignment and then a simulation.